I'm Bob Duhamel, and by popular demand we're going to take another look at the analog oscilloscope. Today we're going to look at the fact that this is a dual trace scope. Most of your analog oscilloscopes are dual trace, which means we have two voltage amplifiers that can give us two readings at the same time. Right now we have it set up as before, so I'm only looking at channel 1, so I have one voltage reading, and there it is on the screen. But what voltage is it? Well, we look at the voltage base here and see we are set at 5 volts, which means that every one of these horizontal lines is 5 volts above the other one. So we have a reading on there, and we know that it's 5 volts per division, but where is our 0 volts? Well, like before, we take our input coupling and put that to ground, and now wherever that line is, that is our 0 volts. So we'll take our vertical position and put that wherever we want it. I'm going to put 0 volts right in the middle of the screen. So now, when I push this back to DC coupling, if the line goes up, it's a positive voltage. If it goes down, it's a negative voltage. So let's set the switch, and it went down by one line. Each line is 5 volts. So 0 volts is in the middle, and it's negative 5 volts. But this scope has two channels, and on this particular scope, this button controls which channel we see. If it's out, it's channel 1, and if it's in, it's channel 2. So let's take a look at channel 2. So there's another voltage reading which is completely different, and it has its different controls, different voltage base, and different input coupling. Its voltage base is set at 5 volts per division, just like channel 1. Let's set the input coupling to ground to see where 0 volts is. And I'm going to do the same thing. I'm going to move that smack into the middle of the screen, set it to DC coupling, and now what we have is it's a positive voltage because 0's in the middle. There's 5 volts. Each small division is 1 volt, 6, 7, 8, just below 9 volts, which is about right because I have that channel hooked up to a 9-volt battery. So with this switch, I can switch between channel 1 and channel 2. Or I can look at both channels at once. The next switch down says mono or dual. Out is mono, shows me one channel at a time, but if I press this button in, now it shows me both channels at one time. I have to remember that my 0 volts is in the middle, and right now channel 1 is the lower channel because it's got a negative voltage going into it, and channel 2 is the upper line because it has a positive voltage going to it. But I see that channel 1 is negative 5 volts, and channel 2 is positive 9 volts. Now I can set my 0 volts for either channel wherever it's convenient for me. So for example, let's say I prefer to put the 0 volts for channel 2 at the very bottom of the screen. I'll set my input coupling to ground and use my vertical position to move that to the bottom of the screen. Input coupling back to DC, and now we see channel 1, 0 volts is the middle of the screen, and I have negative 5 volts. Channel 2, 0 volts is at the bottom of the screen, and I have positive 9 volts. The next button below that says Alt and Chop. What that does is control how the two channels are displayed on the screen. To see a difference, I need to slow down my time base, so I'm going to slow that way down. And right now it's in the Alt mode. If I slow it down more, you'll see the difference. I'm going to move my 0 volts in channel 2 back to the middle. A little tricky with it this way, but there it goes. And back to DC coupling. So channel 1, 2, 1, 2, 1, 2. So slowing it down, we can see it's actually showing one channel and then the other channel. For looking at slow sweeps like this doesn't work very well because it's hard to follow. But what I can do is set this to chop, and it's going to jump back and forth between channel 1 and 2 rapidly, and therefore now has two separate lines. And so if I have something that's happening slowly that I want to monitor at a slow speed, I can see both channels at once. And I can take channel 2, and you can see I'm changing the voltage on channel 2 as it goes by. And now I will change the voltage on channel 1 as it goes by. So we can see them individually. And so if we're sweeping slowly, because we want to see something that's happening slowly, we want to have it in the chop mode so it goes rapidly between the two channels. But if I change my time base, I'm going to take this up to a very high speed. Now as it chops back and forth between the two channels, we get this dashed line effect. So at higher sweep rates, we want to have that in alternate mode. Now let's see what happens when we put an alternating current signal in here. Go ahead and bring that up with the function generator. And so that we can see what's happening, let's bring up the sweep rate. And now I have a 1 kilohertz sine wave going into channel 1. And let's adjust our center there. Seems to have gotten off just a little bit. Back to DC coupling, and we can now see that I have a sine wave on channel 1 and still 9 volts DC on channel 2. Now notice I have both of my inputs to DC coupling. The coupling doesn't mean that DC is for measuring DC and AC is for measuring AC. When we have it at DC coupling, I can see if there's any DC mixed with my AC. I don't see any there, but if there were, I'd be able to see an offset. So at this point, AC coupling and DC coupling doesn't make any difference, except if I do put channel 2 to AC coupling, it blocks out the DC coming from my function generator and we don't see anything. So if you're measuring DC, yes, you must have it to DC coupling. But measuring AC, it doesn't really matter unless you are trying to filter out some DC in the system, which we showed in the previous video, so I'm not going to show it now. So I have an AC sine wave on channel 1 and DC on channel 2. Both are set to DC coupling. Same sweep rate, of course, because we only have one time base for both channels. So there's two completely different signals, one AC and one DC. There's our 9 volts DC on and off here as I play with the battery. And then our AC sine wave that I can change the frequency. There's kilohertz, 2 kilohertz, 3 kilohertz, back to 1 kilohertz. So now let's put a signal from the function generator on channel 2 and see how we can compare that. Take off the DC, and now here goes something going into channel 2. Well, it looks completely different. We can now see the 1 kilohertz on channel 1 and some other frequency on channel 2. And if we look at it, looks like we have twice as many peaks on channel 1 as we do on channel 2, so it looks like channel 2 is 500 hertz compared to 1 kilohertz in channel 1. Now what we can do is we can superimpose them like this if that's useful, or we can set channel 1 to ground. We lost our trigger lock because we're triggering on channel 1, but that's no problem. I just wanted to move channel 2 down to here. Actually, that's channel 1, right up to there. Put that back on DC coupling, and let's move channel 2 down to here so that they're completely separate. So now we see our 1 kilohertz on the top and our 500 hertz on the bottom. We can also see that there's a difference in phase. If I bring this back up to 1 kilohertz, now the two signals are happening at the same time, but if I introduce a little bit of delay in the second channel, it jumps out of lock there sometimes, but we'll just look at it when it's locked in. There we have that. So if you look carefully, you can see they're not happening at quite the same time. Well, we can see it better if we superimpose them on each other. So let's move one channel to the middle, just our triggering so we can see that, and bring that up to the middle. DC coupling. Now let's bring this channel down to the middle, back to DC coupling, and you can see that there's a slight delay between one and the other. Let's increase that so we can see it better. So right now, if we look, let's just look at one channel here and look at our phasing. We have 0 here, 180, 360 degrees. So two lines is a complete wave, or 360 degrees. So if we start here at 0, 90 degrees, 180 degrees, 270 degrees, 360. So if we flip this over here, now we can see that channel 2 is happening 90 degrees after channel 1. And if I increase my phase delay even more, now they are 180 degrees out of phase. So we can superimpose them and check their phase angle against each other. And now getting all the way around to get closer and closer, and there they are, 360 degrees out of phase, which means they're back in phase again. So I can bring channel 1 up and channel 2 down, and so we can have them either lined up or not lined up. So that's basically what we have with a dual trace scope and what you can do with that. So we can look at two different signals at one time. We can either superimpose them or separate them out. We can look at it, one AC signal and one DC signal. We can mix and match them, and that's what we can do with a dual trace scope. Another thing you can do with a dual trace oscilloscope is you can set it up so that one channel handles our horizontal and the other channel handles our vertical. In other words, it's a voltage measurement each way, and we play one channel against the other. Right now I have two 1 kilohertz sine waves going into each channel, and I'm going to press this button, which sets us up to XY mode, meaning that one channel is our horizontal axis and the other channel is our vertical axis. Let's go ahead and press that button and see what happens. Well, that's not too awfully exciting, just a straight line there. Let me reposition things toward the middle, but we can play around with that a little bit and see what happens. What's happening is that we have both channels in sync. At one time the beam is going to the right and down, and another time the beam is going to the left and up, so we end up getting this diagonal line. Let's start making some small changes to one of the frequencies and see what happens. We have 1 kilohertz going in one channel and 1.00001 kilohertz going into the other channel. So there's a very tiny difference in the frequency, and we see that that's becoming a circle and it's opening up. Let's speed that up a little bit. Every time I change the frequency, it tends to reset. That's just the nature of this function generator. So as I increase the frequency difference, we get that effect there. Let's make some bigger changes. So as the frequency gets different, this is a 1 hertz difference here, and a 20 hertz difference. And there's your background for your science fiction movie. So this is what's called a Lissajous pattern, and as we change our frequency even more, we can get some even more interesting patterns out of this. Let's crank that up a little more till we get it to synchronize and see what we get. Let's make a 100 hertz difference. Oh, that's interesting. How about 200 hertz? Oh, all right. 300 hertz, 400. There's a 500 hertz difference. So we have it sweeping back and forth at 1 kilohertz and sweeping up and down at 500 hertz. And the synchronization causes us to get this little pattern here. So we get all sorts of interesting patterns. Don't know how useful these are, but they look cool. Putting channel A against channel B has some uses in testing radio circuits that we'll see at some other time. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.